on the age of data, visualization, the revolution. Visualizing the revolution. It's going to be a really interesting night, I promise you. Data visualization is a relatively new discipline. It's really been brought upon us by this fantastic amount of data, our ability to collect and analyze data and pouring in through the windows, the walls, everywhere, and really has made a revolution. So the word is appropriate. Today's data sets are almost unimaginable in size, scope, what they're about. And one article I recently read actually mentioned, and maybe one of our first speaker, Chris, will talk about it, that every day we're producing 2.5 quintillion bytes of data, 2.5 quintillion. We can talk afterwards to understand how big that number is. And that's really extraordinary. It's just unbelievable what's happening today. And you can imagine that these huge data sets are a real boon and exciting for scientists as well as companies and everybody else, but certainly for scientists, which you'll hear about tonight. But only if we can figure out a way to use this data. And of course, data is just data until you can figure out how to use it, how to visualize it basically, how to do something important. And in the end, we're taking these massive data sets to look for something perhaps tiny that you won't see easily, essentially pulling that elusive needle in a haystack out of this tremendous data sets. Data visualization works to really solve problems by offering new and comprehensible ways of looking at data sets that are so large and so complex that previous types of data processing are simply inadequate to the task. If it's done right, data visualization makes it possible for us to see very minute details, to look at trends that you wouldn't otherwise see, outliers, patterns that might otherwise be entirely invisible. And that makes data visualization a really crucial tool for scientific discovery, especially the kind of work we do here at the Carnegie Institution for Science. Our investigators are leaders in astronomy, global ecology, in earth and planetary sciences and developmental biology, fields that require massive amounts, enormous amounts of complex, interrelated data. So data visualization makes it possible for us to accelerate our work by using computation as really as a third leg of discovery. You hear about experiment, you hear about theory. We're now seeing a real transformation in thinking about computation and data as that third leg in discovery science. And visualization itself makes it possible for us to better understand many, many things in science, the cosmos, the shape of the cosmos, to investigate deep into the interiors of planets, which you'll hear about tonight, and to delve more deeply into the origins of life itself. So I'd like to introduce to you who's going to be on stage tonight. Our guest tonight, our featured Chris Johnson. He's made some extraordinary contributions to this field of data visualization as well as computation. He is the founding director of the Scientific Computing and Imaging Institute at the University of Utah, appropriately called SCI. The Institute is recognized around the world as a leader in visualization, scientific computing, data analysis, image analysis, etc., in a broad range of scientific and disciplinary fields, not just science, as well as medicine, and work that ranges from development of individualized models of the human heart to the creation of a perfect digital version of Michelangelo's David. At the university, Dr. Johnson serves as a distinguished professor of computer science and a faculty member in the Department of Physics and Bioengineering, which you call a real Renaissance man, speaking of Michelangelo. He is a fellow of the American Institute for Medical and Biological Engineering, the American Association for the Advancement of Science, the Society of Industrial and Applied Mathematics, and most recently the IEEE. He's also won a number of awards throughout his distinguished career, including the IEEE's Sidney Fernbach Award for his outstanding contributions and pioneering work introducing computing, simulation, and visualization into many areas of biomedicine. After his presentation this evening, Dr. Johnson will join in a panel discussion with two of our own Carnegie scientists. Shaunna Morrison is a mineralogist in our geophysical laboratory. Our research focuses on data-driven approaches to characterizing the coevolution of the geosphere and the biosphere, and on applications of advanced analytics to Earth and planetary systems with a particular emphasis in mineral relationships. She has also used sophisticated data mining techniques to understand the mineralogy of Mars and other of our neighboring planets at an unprecedented scale. Our other panel member, Juna Kollmeier, is an astrophysicist at the Carnegie Observatories in Pasadena. He is also the director of the 5th generation of the Sloan Digital Sky Surveys, a massive project that aims to map the universe and understand it in much deeper detail. Her research is primarily focused on the emergence of structure in the universe, and her work lies at the intersection of computational, theoretical, and observational astrophysics. Their discussion tonight will be moderated by Madeline Sophia, who is an associate producer on National Public Radio's Science Desk. She hosts the show Maddie About Science, which takes viewers behind the scenes to learn more about leading researchers and their work. And before embarking on her career in science communications at NPR, Ms. Sophia earned her PhD in microbiology and immunology from the University of Rochester. Like you, I am really eager to hear tonight's featured speaker and the distinguished panel, so please join me in welcoming Chris Johnson.
Here we are. Thank you, Eric, and thank you all for coming out this evening to hear a little bit about visual analysis. And when I give these talks, I like to give a little bit of background from where I came from in terms of the University of Utah, because I don't think that most people know the pioneers of computer graphics. Many of them came from the University of Utah. This is a composite of some of the pioneers. David Evans and Ivan Sutherland started our Department of Computer Science back in 1965. Ivan is known as the father of computer graphics and received the Turing Award for his work in computer graphics. Other of our famous graduates you might have heard of before. I think you use their products almost every day. Number 3 up there is John Warnock. John created PostScript and then founded Adobe and was the president of Adobe for a number of years. Another of our graduates, number 4, is Ed Catmull, who with Steve Jobs co-founded Pixar. And is still the president of Pixar. You might have also, especially the older members of the audience, might also have heard of number 7, Nolan Bushnell, who created Pong, the first video game. And then Atari, which he sold in the 1980s. And then to the younger audience, then he created Chuck E. Cheese Pizza Time Theaters. But here we're here to talk about today and the age of data. And some of you may have seen one of these composites of how much data we are creating every minute of the day. And so it's just astonishing. If we look up here and see that we have 4 million YouTube videos per minute every day. We have down here, let's see if I can get my here is my second. All right, we'll stop using the pointer and just start. You'll see that there's over almost 4 million Google searches every minute. And one that I was a little confused about was up here at the Weather Channel, where there's supposedly 18 million requests for the weather every minute of every day. And I thought about that for a while, and then I thought, that doesn't really make sense. But then, if you think about how many of you have a weather channel or station on your phone that automatically finds out the weather for you, you're not searching, but your phone is searching every day. And Eric stole my next slide, which was that every other day we are creating 2.5 exabytes of data. He used quintillions, which is another name for that. So that's 2.5 times 10 to the 18th, so 10 followed by 18 zeros every day. That is equivalent to the amount of data that we created every other day since the beginning of mankind started recording things with books and whatever, till the year 2000. So we are on this enormous exponential curve. And we call it the exascale. So we're living in the exascale every day. And we are soon to go over that to the next scale. And does anybody know what the next scale is called by any chance?
The exascale.
It's called the Zeta scale. So we're about ready to have Zeta scale amounts of data. So we are very visual creatures. More than half of our brains are devoted to image processing. Unlike whales, I learned recently, where 80% of their brains are devoted to hearing and sound. So for us, one of the best ways that we can understand and make use of this data, which is really one of the grand challenges of our century, is if we can map that data into something that our visual system can better understand. And so we spend a large amount of time trying to come up with new techniques, new mappings, new abstractions, new ways to map that abstract data into something that our visual systems can understand. And what you see up here are a number of visualizations that we have created with our collaborators. That middle one is a visualization of one of the largest simulations of a spiral galaxy forming. The one to the right in the middle is one of the largest combustion simulations. The second one on the top left is one time instant in visualizing the magnetic field of our sun. We also have in this bottom right here a multi-window visualization that's all interconnected for cancer genetics. And what I'd like to do is to just give you some stories about some of our collaborations with these different researchers and how we have created visual tools and techniques and algorithms to help them, enable them to better understand their science. I'll start with one of our recent collaborations, and one that certainly Carnegie and Juna is very interested in, is space and astronomy. I think we're all enamored with space and astronomy. And this is called Open Space. It's a collaboration between a number of researchers throughout the world, including researchers in Sweden, led by Anders Ginnerman, the American Museum of Natural History at the Hayden Planetarium, Carter Emmer, researchers at NYU, and also at NASA, as well as the Scientific Computing and Imaging Institute. And it's really about, we've all gone to those planetarium shows where we see these more amazing, each year displays of what's there, but that's all pre-done canned data. And NASA came to us and said, can you do this with real NASA data? Can you create visualizations of our space missions, of the astronomy data that we're collecting, of simulation data? And the answer was, we think so. And we are in the process of doing it, and it's called Open Space because we've made it all open source software. So if you go to that link down there, you can download this, use this, modify it, do whatever you want. So this is one of our initial demos of getting Open Space running. This is Gene Kane, who is one of the software developers, and what he's doing is he's on a large multi-touch visualization table, and he's showing you how easy it is to navigate around the solar system with Open Space. You should note that all those stars are in the right positions, and that the trajectories that you're seeing are all calculated with the same mathematics that NASA uses to plan their missions. What we're doing now is we're going to zoom in, and we're going to pull down real-time satellite imagery from NASA, and we are, of course, going to zoom into Salt Lake City. And where you see is the Great Salt Lake that's there. And so we're zooming in. We're also going to now project this onto what we call a power wall, which is 36 30-inch monitors where we get much higher resolution. We can also project this onto planetarium domes and other systems as well. So what Gene is going to do, though, is he's going to take his hands off of the touch table. And did you see what was happening? It was moving still when his hands were not touching it. And that's because we are getting this real-time data and the Earth is spinning. And so this is really exciting that we can do this large-scale, high-resolution astronomical data and interact with it. Most recently, we have put in the entire Sloan Digital Sky Survey, which is a mapping of the galaxies throughout our universe. And here is Gene again He's slowly rotating this because if you rotate it too fast, you can get a little queasy seeing this. And again, we're going to pop this up on our screen.